In this lecture, we're going to start and learn about dynamic memory allocation. And this is a technique we can use to start using heap storage that we have in the memory map of our C++ program. We can use that to get additional memory we can use and do stuff if stack memory isn't enough for our purposes. This is how we have been using pointers so far. For example, we have a variable, we set up a pointer, and we store the address of the variable n. So we can go ahead and use this pointer to manipulate the variable or do all kinds of crazy things. If you go down here, we have a pointer p number 1, and we have a number 1 variable, and we can store the address of number 1 into this pointer. It's really the same thing like we have on top here, but the pointer is not initialized at declaration here, and you have to make sure you put in valid data. And one thing I haven't really stressed enough is that it is really bad to try and use a pointer that is not initialized. For example, here we have p number 2, which is a pointer. It is not initialized. It contains junk, and we try and write into it. Okay, so try to think about what we really are doing here. This is a pointer that we have set up. We haven't really initialized that. So it's going to contain whatever address is possible. It can contain an address that is used by another program. It may contain an address that is being used by the operating system. It's not your address to mess with. And here we are actually trying to mess with it by storing in a 55. So this is going to cause a crash, possibly, or even corrupt data that is being used by other people. So don't do this. Another thing is to try and use a pointer that is initialized to null. For example, here we have a pointer p number 3, and it is braced initialized. This is going to initialize it to null pointer, but we are trying and storing in a value here. So this is also going to be bad. It's not guaranteed what you're going to get. Actually, C++ doesn't give you any guarantees. This is called undefined behavior. So you're going to get a crash, and don't do it. As a good practice, the first thing you should do is initialize your pointers before you use them. You can initialize them with null pointer, and make sure that you are modifying valid addresses into those pointers. If you don't know what is in a pointer, don't use that pointer because bad things can happen. Okay, rule number 1, don't try to use a pointer that you didn't initialize. Rule number 2, don't try to work with a pointer that is pointing to null PTR. That's going to give you bad things you don't want to really deal with. Okay, so far we have been using memory that lives on the stack section of our memory map. We were using variables that we have declared in the main function. We were using variables that we have declared inside some functions. And that's all stuff that live on the stack. Now we want to see how we can use the heap. Okay, let's take a closer look at our memory map. We have the stack, we have the heap, and the differences between these two guys are laid out here. The stack memory is finite, so you don't have infinite memory. But the same is true for the heap, but heap is additional memory that you can use if you don't want to run out of stack memory. For stack memory, the developer isn't in full control of the memory lifetime. So if you declare something on the stack, for example, if you say int var1 and you initialize that to 23, you don't control when that variable is wiped out of memory. The variable is going to be killed when the scope in which it was declared is going to run out. And you, the developer, don't really say when the variable dies. And sometimes you really want to control when your variable dies. So this is a limitation we have with the stack memory. Okay, so for stack memory, lifetime is controlled by the scope mechanism. We just said that. For heap, the developer is in full control of when the variable comes to life and when the variable dies. And this is a benefit you might have with heap storage, and you might want to use this, and we're going to see how we can use that in the next few lectures. Okay, so make sure you understand the difference between stack and heap here. If you look at the example here, we have a variable which is called locus scope var. It is stored within this block delimited by the curly braces, and the variable is going to come to life when this statement is executed, but it is going to die when we hit the closing curly brace here. So the lifetime of this variable is controlled by the scope mechanism. but it is possible to use dynamic memory or use memory on the heap. And we're going to see a syntax you can use to do that. The first thing we want to do is to set up a pointer that is going to be pointing to that heap allocated memory. The way you do that, you set up a pointer. Here we have p number 4. We initialize it with null ptr. But what we do to allocate memory is the second statement here. We say p number 4 and we say new int. The moment this statement is going to be executed, the operating system is going to allocate a piece of memory on the heap. The memory is going to be large enough to accommodate for an integer, so it's going to be 4 bytes long. And it is your memory now. Your program can use it to do whatever it wants, and no other program on the system can use this piece of memory. So it is going to be yours until you explicitly return this piece of memory to the system, and we're going to see how you can do that in a minute. Once this memory is yours, you can use it. You see here we are dereferencing the memory and storing in a 77. And if we're trying to print this 77, we're going to get it printed down. Okay, this is how you can use dynamic memory. And when you do this, things are not being stored on the stack. Things are being stored on the heap. I really hope you understand this because it is very important. Okay, so here is our view of stack and heap. So if you use new to allocate for memory, stuff are going to be stored in this heap section here of your memory map. Here is another example to try and understand the lifetime of our variables. Localvar again is limited to this scope. It is going to come into life when this statement here is executed, and it is going to die when we run out of this scope here. So if you try executing code out of this scope, localvar is no longer going to be available. You can't use it. But that's not the case for local ptr var, because this is a pointer. It lives on the heap, and if you go out of this scope, the memory is still going to be yours. So if you have a way you can access it and use it, you're going to be able to use it, and it is going to be yours until you decide to return it to the operating system. So we have been talking about returning the memory to the system. How do we do it? Well, you use the delete keyword in C++. Here we have our memory, which is allocated using new int. So the operating system is going to give us a new piece of memory. It is going to be 4 bytes because we're going to store in an integer, and we are going to be pointing to that memory through p number 4 here. We can use this memory however we want through the referencing and do all kinds of crazy things. And when we are done with this memory, we are going to say delete p number 4, and this statement is going to return the memory to the operating system. The memory is no longer going to be ours after this statement. And a good thing to do after you release your memory is to reset it to null ptr so that other people know that you don't really have any valid data in that memory. Because if you try to use a deleted memory section, bad things are going to happen. That's not going to be your memory. We're going to fall into the same problem of trying to use an uninitialized piece of memory. Don't do that. So whenever you release memory, also reset it to null ptr to play it safe. We can also initialize our pointers with dynamic memory when we declare them, and this is how you can do it. We say p number 5 and we initialize it with new int. This is going to give us a new piece of memory on the heap, and it is going to be pointed to by p number 5. We get the same thing here, but here we are just putting in new values in p number 6 and p number 7. The memory locations on the heap are going to be containing 22 and 23 for p number 6 and p number 7. And here we have a few examples of how we can print the contents of these memory locations on stdc out. And after you are done using your heap memory, you're going to release it using the delete keyword, and you are going to reset that to null ptr to really play it safe. This is how you should use dynamic memory allocated on the heap. Another thing you should know is that it is really bad to call delete twice on a pointer. So here we have a memory location that we allocate on the heap. We stored this in a pointer, and we are trying to use it here in stdc out, reading whatever is inside. And if we delete it for the first time, that's going to be cool. It is going to be returned to the system. But if you try to delete it for the second time, you're going to get a crash Don't do this. This is really bad. Okay, now that we have a slightly clear idea about pointers and dynamic memory allocation, I think it is time we went to Visual Studio Code and actually played with a few of these concepts. Here we are in our working directory. The current project is dynamic memory allocation. We're going to grab our template files and we're going to put them in place, dynamic memory allocation. Let's do that. And we're going to open this in Visual Studio Code. The first thing we're going to do is review how we have been using pointers so far. We have been using them like this. We had a variable stored somewhere on the stack. Again, this is the stack memory that we are using here. And we stored addresses of some variables in our pointers, something like this. And we could go through the pointer to manipulate that memory location. For example, we can print the address of that memory. We can even dereference and print the value in here by doing something like we do here. And we are not printing here. So let's say that and say P number. We can do something like this. And we have been doing this quite a lot so far. We can also have a piece of memory that is uninitialized. And we store the address of some variable in that piece of memory, and we can do the same thing. For example, if we print P number 1, we're going to get the value 12 printed out here. And we could run this, so let's try and do that. We're going to bring up a terminal first and close this pane so that we have some breathing room. And we are going to build with GCC like we always do. We're going to build successfully, we're going to clear and run Rooster, and we're going to see that we have these things printed out here. The variable we have in here is 22, so we're going to get that if we print the variable directly. If we print pointer, we're going to get the address printed out. We can also go through the address of operator to print the address of this variable here. But we can also print our value through dereferencing our pointer, and we can get access to it here. Down here, we have a pointer that is not initialized, so it will contain a junk address that you shouldn't really use. But we're not going to do that because we're going to store in the address of number 1 here, and we can manipulate the value here through the pointer using the dereference operator here. And if we print this P number 1, we're going to get 12 printed out. This is pretty cool. Okay, so this is how we have been using pointers so far. Let's comment this out because we're going to see some other things. Okay, before we really look at how dynamic memory works, we are going to show you a few bad things you need to be aware of. So let's put in a piece of code for us to play with. And here we are saying that writing into uninitialized memory is really bad. So here we have a pointer. It is uninitialized, and we are trying and directly write into it through dereferencing. And this is going to be bad. You see that Visual Studio Code is not complaining. It thinks that we know what we are doing here, and it's not going to warn us. But this pointer could really be pointing anywhere, including operating system specific memory. And here you may be trying to modify things that your operating system is going to need. So clearly, the operating system is not going to be happy about this, and bad things can happen to this program. So now we have this memory location. We're going to try and write into it, and we're going to see what happens if we run this program. For now, let's try and take this little section here and comment it out. And we want to see what happens on the program here, the code here that we might want to run. Let's try and build it with GCC. We're going to run the task to do that. The build is going to be good. You see that we don't even get a compiler error. And if we're trying to run Rooster, you see that the program is going to try and run, the operating system is going to say, this guy doesn't know what they are doing, and I am going to close them. You see that it's not even running this statement here. Let's go on top here and put in an stdc out statement so that we can really see where this program is failing. Let's say that stdc out writing in the 55. Okay, so this is what we have. We have a few statements added in, and we want to see if we actually get to run these two things to see where the program is actually failing. We are going to build it again with GCC, and we are going to clear and run Rooster. You see that it's going to say writing in a 55, but this statement here is going to fail because we are trying to write into memory that is not ours, and the operating system is going to stop us. So our program is crashing and it is terminating before it even runs the things that are down here. Hopefully you can see how bad this is. You have designed your program to do things, but it is going to stop without having done any of the other things that you have designed below. So this is really bad. And another bad thing is that you might have allocated some dynamic memory beforehand, and your program is going to end before it even releases that memory properly and returns that to the operating system. So this is bad. You don't want crashes in your programs, and don't ever try and use and reference memory that you haven't initialized. This is one bad thing. We're going to comment this out. I hope you really know how bad this is. And we're going to go down again and uncomment what we had done here. And it's going to be another bad thing because we are trying to write into memory initialized to null PTR. Okay, here we have a pointer. It is called P number 3, and it is initialized with null PTR. You can think of PTR as an address that says, I don't have any valid thing in me, don't use me. That's what null PTR is saying. So we have the pointer initialized to PTR, but we are trying to store something in here. And you can imagine how bad this is. This is memory that isn't really valid. The memory itself is saying, I don't contain anything valid, don't try to use me. And if you try to use it, bad things are going to happen. So if we try and compile this program, it is going to compile. The compiler is not going to stop us to do something like this. And these are some things you need to be aware of in C++. But if we try to run it, you're going to see that we are also going to get a crash. Again, let's try and put a statement in front of this failing line. And below this line, I can say done writing. And I can do std_endl here. And build the program so that we can see which std statements run and which don't after our program crashes. So we're going to clear. The build is good. And run rooster, you're going to see it's going to say what it's doing. It's going to try and fail, and the operating system is going to kill this program because it is crazy. It is doing what it shouldn't really be doing. So this is something bad. Don't do it. Be aware of this thing. Okay, we're going to comment this out and actually look at how we can dynamically allocate memory from the heap. And we're going to put in a piece of code to play with that. It's not really complicated. We have a pointer. We initialize it with null pointer to say that this pointer doesn't point to anywhere valid. Don't use it. And we are calling new end. When we do this, the operating system is going to give us a new piece of memory on the heap. This piece of memory is going to have the size enough to contain an int, so it's going to be 4 bytes in memory, and we are going to be pointing to that piece of memory using the P number 4 here. This is what we are trying to say here. The moment we do this, we own this piece of memory, and nobody else on the operating system can use it. So that's something you should know. Once you have it, you can manipulate it through the pointer here. So here we can go through the reference operator and store in the 77. And if we print it out, we're going to get that printed out here. Okay, this is really cool. This is the first time we use heap memory, and I am excited about showing you these things. We're going to try and build this program, and the build is going to be good, and we are going to clear this. And if we run rooster, we should see a 77 printed out. Let's do that. We're going to get our 77, but this 77 is stored on the heap now. It is not stored on the stack, and this is really, really cool. We can control when this variable comes alive by allocating memory on the heap, and we exactly control when this variable dies if we want. And we're going to see how we can kill this variable from memory. But for now, just take a moment and appreciate how cool it is to be able to allocate stuff on the heap. It is really cool. Now that you have used the memory, it is really time to return it to the system because we have no more use for it. The way you release memory to the system is to call the delete keyword and say the pointer pointing to the memory that you are trying to release to the system. So we're going to say P number 4 here. Let's bring this down a little bit so that you can see the entire story. So we have a pointer here, and it is pointing to dynamically allocated memory from the heap. This memory is 4 bytes large because it stores an integer. We have it dynamically allocated. We use it here, and it is time to return it to the operating system. Okay, I hope this is clear. The moment you call the delete keyword, now the memory is going to be containing some junk, and you don't want to really use that anymore. If you try to use it, it's not your memory, you're going to run into trouble. So for example, after we delete this memory, if we try to use it, I'm going to show you here, I think I can. Let's say P number 4 and store in something. Notice that we are using the dereference operator, and let's try and put in a 45. Why not? So let's build this with GCC as we always do. It is going to build. The compiler is not going to stop you from doing something like this, writing into memory that you have already released to the system, but we're going to see what happens. So run rooster, and it is going to say done writing, but you see that the program has really crashed. Because here we are trying to write into memory that we don't really own, and this is bad. Don't do this. So the moment you delete the memory, or the moment you return the memory to the operating system, it is good practice to reset that memory to null PTR. So we're going to say P number 4 and make sure it contains null PTR. At least when we do this, other people have a chance to check and see that that's valid memory before they use it. That's the use of resetting your memory here. So this is something you should do. Again, the flow to use dynamic memory is really simple. You set up a pointer that is going to point to your memory. You're going to allocate the memory from the heap using the new operator. You're going to specify the type you want to allocate memory for. The operating system is going to give you that memory, and you're going to be pointing to that memory with your pointer. You are going to manipulate that memory using your pointer and doing all kinds of crazy things. And after you are done with that memory, you're going to release it to the operating system. And please remember to reset your pointers after you have deleted them like this. That's going to make your life a whole lot easier, and other developers are going to thank you for doing this when they get to use your code, because your code is going to be much safer to work with. Okay, let's comment this out and show you another example of what cool things you can do with dynamic heap memory. We're going to go down and put in a piece of code and show you that you can actually dynamically initialize your pointers at declaration. This is something you can do. The first one is not initialized, so it's going to contain junk value. P number 5, if we try to print it, we're going to get some junk address printed out. P number 6, we're going to dereference it and print the value inside, so we're going to see that. And we can do the same thing for P number 6 and P number 7. After we are done using the pointers, we are going to release the memory here, and notice that we are resetting the pointers to null pointer to say that they don't really contain anything useful. Don't use them. Make sure you have something valid in before you use them. This is the meaning here. If we try to run the program, you can guess what we're going to see. So try and guess. And we're going to build. We're going to build successfully. We're going to clear, not clear. And we're going to run rooster. And we're going to see that P number 5 contains some junk address. Okay. And if we try to dereference it, we're going to get a junk value. This is really not useful. Don't use this value because you didn't put this value in the first place. You're going to see that P number 6 is going to point to some other address, but we're going to have a valid value inside because we have put that in at initialization here. The same is true for P number 7. It's going to point to some address, and we're going to have 23N because we put in our 23. This is how you really use these pointers. Another thing I want you to know is that even if we have called, delete, and reset these pointers, they are still available for use in our program. So if we want, we can reuse these pointers. So for example, P number 5, we can take it and use it to allocate new memory. So we can say new int and store in 81. Why not? Okay, so we can go down here and use that. This is going to be valid C++ code. Okay, take a moment and look at it. It is P number 5, not P number. And Visual Studio Code is going to take this because it is valid C++ code. The memory has been returned to the operating system, and the pointer has been reset to null PTR, but we can reuse the same pointer to allocate new memory. So we are allocating new memory on the heap. The memory is going to be 4 bytes because it is going to contain an integer, and we are using this pointer to point to that new memory. So this pointer is being reused. It was pointing to the memory that we allocated here, which was uninitialized, and we are using that to point to new memory location on the heap. I really want you to understand these things because many beginners get them wrong, and it is hard to correct these things in your mind once you have a wrong idea about them in the first place. So make sure you understand this. So if we print this, we're going to get the 81 printed out, but we have allocated new memory. We have to remember to release it again. So we have to come and say delete P number 5, and we need to reset it to null pointer. And we're going to do that right here. Once we do this, we're going to be playing it safe. Let's try and run and see that we see the 81 printed out. We're going to build with GCC. The build is going to go through, and we are going to clear and run rooster. And you see that we see our 81 and we don't have any crazy crash. For example, to prove that we don't have a crash, we can say that our program is ending well. And we're going to know if the program has actually reached the end before it dies. We're going to build again with GCC, and we're going to clear and run rooster. And you're going to see that the program is ending well. The other thing I want you to see is that it is really bad to call delete twice on a pointer. Again, it is really bad to call delete twice on a pointer. Don't do that. Okay, we're going to see an example of that here. So we're going to allocate new memory using P number 5. Why not? So we're going to say P number 5, and we're going to say new. And we're going to allocate new memory on the heap, and we're going to store in a 99 in that memory. We can print out the 99, so we're going to say, and after we are done using this memory, we are a good C++ citizen, so we're going to call delete and say P number 5. Okay, this is good. It is going to work. If we build and run, we're going to get what we expect. We should get a 99 printed out last in our program before it ends. And we see that printed out here. Program ending well. This is really cool. But if we try to call delete twice and say P number 5 again and try to build, you see that the compiler is not going to stop us because it thinks we know what we are doing. So this is something you need to be aware of in C++. If we run this program, you're going to see, the program is not going to end well. The C++ runtime or the operating system is going to get here and see, this guy is trying to release memory twice, and I don't do that. This is a bad program. I am going to kill it, and it is going to be killed. The bad thing again is that anything you have in your program after these lines is not going to run because the operating system is going to kill your program at this line here. So if you had memory allocated that you planned to release later on in your program, your memory is not going to be released because those statements to release the memory will never be run. This is where the program is going to be killed. The operating system is going to see that you are a rogue program and it is going to kill the program. So don't delete your memory twice. This is something you should really watch out for. And you might think, I know this. Why would I call delete twice in a single line here? Well, you may not do it like this, but your program might have multiple files where you have pointers pointing to the same memory. And if you try to delete that memory twice, you're going to get this error, and this is really good. So watch out for these kinds of things, and we're going to see different ways you can use to really make sure you are doing things right in C++. This is really all we set out to do in this lecture, giving you first-hand practice on how to do dynamic memory allocation. I hope you found this useful. We are going to stop here in this lecture. In the next one, we're going to learn about dangling pointers. Go ahead and finish up here and meet me there.